I'm taking here 250 milliliter of water, and I'm also taking 250 grams of sugar. And I'm telling both are equal. But does it make any sense? Actually, no, because both the units are different. But if I say E is equal to mc squared, then this makes a sense because both the sides of the equations are having the units of energy. This made the study of dimensional analysis into use. Actually, the dimensional analysis is the study of relationship between the physical quantities with the help of or in the terms of dimensions and units of measurement. So today's topic is the application of dimensional analysis. There are three applications which we are going to study today. So the first application is we can convert physical quantity from one system of unit to another. This is done when the magnitude of the physical quantity remains the same in both the set of the units. Now, let us consider if Q is a physical quantity. Let U1, U2 be the two sets of different units. N1 and N2 be the numerical values of 1 and 2. Now, what do we get? Q equals to N1, U1 equals to N2, U2. Let M1, L1, T1. This be the size of mass, length, and time in the first set of units. And let M2, L2, and T2 be the sizes of mass, length, and time in the second set of units. Let the dimension of the physical quantity Q be M, L, T, M to the power of A, L to the power of B, T to the power of C. We are not knowing the dimensions of mass, length, and time. Now, N2 is equal to N1, U1 upon U2. So, what will be here? U1. U1 will be equal to M1, L1, T1 with the powers of A, B, C respectively. U2 will be equal to again M2, L2, T2 with the powers of A, B, and C respectively. Therefore, N2 equals to N1. We can write like this, M1, M2 to the power of A, L1, L2 to the power of B, and T1, T2 to the power of C. So, with the help of this equation, we can easily find, we can easily find here the second set of unit in the terms of the first unit. It will be clear if we do this with the help of an example. Suppose a question comes to you that convert 1 Newton in dyne. Now, this Newton is of course your SI unit of force and dyne is the CGS unit of force. Both are the units of force. Units of force in different set of units. So, in the case of SI, we take into N1. This is given to be 1 Newton. N2 is not known to us. Then M1 equals to 1 kilogram, which is also equal to 1000 gram in CGS. Then L1 will be equal to 1 meter, which is again equal to 100 centimeter in CGS. And T1 will be of course 1 second. Here M2 will be equal to 1 gram. L2 will be equal to 1 centimeter and T2 will be equal to 1 second. We can see that in both SI unit and in CGS, the unit of time is second. Now we need to convert the unit of force from Newton to dyne, and we have to know 1 Newton is equal to how many dynes. So how to proceed? Now, N2 is equal to N1. Here we are getting here M1, M2 to the power of A, L1, L2 to the power of B, T1, T2 to the power of C. Now the dimension of force. Force is what? Mass into acceleration. Dimension of mass is m. Dimension of acceleration we have studied. It is equal to LT minus 2. So the dimension for force we can write MLT minus 2. Now we can see here that from this two equation, equation number 1 and equation number 2, that we can see here that A will be equal to 1, B will be also equal to 1 and C will be equal to minus 2. Now putting the values over here, we get here F equals to MLT minus 2. We have to find now the unit of force in CGS. So, N2 equals to, N1 is already given to us 1. M1 is your 1000 gram. This 1 gram. A is your 100 upon 1. This is again B 1. And then 1 upon 1, C is your minus 2. So what we are getting now? N2 equals to 1. Here you are getting 10 to the power of 3. Here you are getting 10 to the power of 2. That means this is equal to 10 to the power of 5. So what we are getting here? That 1 Newton equals to 10 to the power of 5 dyne. So we have seen here that the unit of force in SI unit was Newton and in CGS was dyne, and we have converted from SI unit to CGS. So whenever we need to convert CGS in CGS unit, we will simply multiply it with 10 to the power of 5. So this is one of the application of dimensional analysis. Now let us come to the second application. The second application is to check the correctness of an equation. Let an equation be V equals to U plus AT. I hope you remember this equation. This is your equation of motion, first equation of motion. Here, V is your final velocity, U is your initial velocity, A is the acceleration, and T is the time. Now, the dimension for V. What is the dimension for V? LT minus 1. Dimension for U, LT minus 1. Dimension for AT. What is the dimension for acceleration? LT minus 2. And then again T. This comes out to be LT minus 1. Now, actually, this is based on the principle of homogeneity. Principle of homogeneity. What does it say? It says that an equation is dimensionally correct only if the dimension of all the quantities which are in the equation, for example, dimension of this V, dimension of U, dimension of AT, all should be same. Here we can see that the dimension of V is coming LT minus 1. Dimension of U is coming again LT minus 1. And dimension of AT is also coming LT minus 1. That means this is correct equation because all are having same dimension. So this equation is correct. Now let us take another example for your concept to be more clear. Let us take the second equation of motion. S equals to UT plus half AT square. Here you can see that S is your displacement, U is the initial velocity, T is the time, half is a number, A is acceleration, and T is again time. So according to principle of homogeneity, the dimension of S should be equal to the dimension of UT, and again it should be equal to the dimension of AT square. Now let us find out whether it's true or not. Dimension of S. What will be the dimension for S? Displacement. That means its dimension will be L. Now, UT. This is your LHS. Now, RHS. Dimension of UT. Dimension of U is again LT minus 1 and then T. So, this will be equal to L. Then half AT square. Half is a number, so it has no dimension. Dimension of acceleration LT minus 2 and here T square. So this again comes out to be L. Now we can see here that here the dimension is coming out to be L. Here also it is coming out to be L. Here also it is coming out to be L. So all the three are having same dimensions. That means this equation is correct. I hope it's clear now. Now coming to the third application. Third application says that we can also derive any equation using the dimensional analysis, derivation of an equation. For this, let us consider a body traveling in a circular path having mass m, and this circle has a radius r, and this body is moving with velocity v. So there will be a centripetal, that means center seeking force. Now we are not knowing that it is, of course, depending on radius, mass, and velocity. But how? Let us consider that it is directly proportional to mvr in the power of a, b, and c respectively. But we are not knowing here the dimensions of m, v, and r. If we put out or take off the sign of proportionality, we get a constant k, which has no dimension. It is a dimensionless quantity. So we get here m to the power of a, v to the power of b, r to the power of c. We are not knowing here a, b, c equals to what? But we are knowing the dimensions for f. F, what is the dimension? M, L, T minus 2. What is the dimension for m? Of course, only m to the power of a, LT minus 1 to the power of b, and r, again length, to the power of c. Now we can see here, this can also be written as k. M is only here one quantity, but L power will be added, b plus c, and then t minus b. Here it is mlt minus 2. On comparison of the both side of the equation, we get a equals to 1, b plus c equals to 1, and c minus b equals to minus 2. This means b equals to 2, and putting the value of b over here, putting this value of b over here, we get again here b, that means 2 plus c equals to 1. So c will be equal to minus 1. Now we are getting three values over here. That is a equals to 1, b equals to 2, and c equals to minus 1. And our equation was f equals to k m a v b c, r to the power of c. So if we put the values over here, what do we get over here? F equals to k m to the power of 1, v to the power of 2, and r to the power of minus 1. That means k mv square upon r. So here we have derived an equation for centripetal force that says that F equals to k mv square upon r. Now we can see here that by using the dimensional analysis, we have derived an equation. So I hope all the three applications are very, very clear to you all. Let us now review each application. The first one, we converted a physical quantity from one system of unit to another. Here we converted, you can see, we took two unit system of units, U1 and U2, and we converted 1 Newton into how much dyne? That comes out to be 1 Newton equals to 10 to the power of 5 dyne. Conversion of one unit to another. Next is your application was to check the correctness of an equation. This is based on the principle of homogeneity, which is again based on the fact that the physical quantity of same nature can only be added. For example, velocity will be added to velocity, and acceleration will be added only to acceleration. So here we check that v is equal to u plus at is correct. Another equation we took, that is s is equal to ut plus half at square. Here also the dimension of each of the quantity was equal, so it's correct. The third application is the derivation of any equation. Here we derive the equation or the formula for centripetal force, which we are getting F equals to kmv square upon r. So now I think that the concept of dimensional analysis is very, very clear to all of you, and we have to apply this in physics in many, many questions and for getting our concepts clear. Thank you all of you.